All right, guys, I'm going to show y'all how to create a model from scratch. So we are going to go over some of the simple stuff like creating the substrate from a cube like we did in the demonstration, but it's worth listening to again. So the first thing that we do when we open up ANSYS is we create a new file, and you're going to click up here. You may not see these coordinate axes right away. You may see that gray screen when you first open. So you're going to click up here on HFSS, and this will open a new HFSS project. I've got a couple of them open over here in my project manager window. Don't worry about this. We're going to be working together on project 5. I'll show you why I have another one open at the end. It's just because it takes a little while to simulate. So let's build this together. We're going to start by clicking up and creating a cubic object. It's a little weird to create. You got to click, drag, and click to create a cubic object. And you can see in our model builder tab, or model builder window, whatever you want to call this window right here, that we've created under the model, we've created a solid. Its material is vacuum. Its name is box1. And this is how we can create it, by using this create box function. The first thing we'll do is double click on box 1. We're going to rename this. This was going to be our substrate. And its material, these are all the materials that we've used. We haven't used any materials, so the list is empty. We're going to click edit. These are all the materials that are available to us. You can search through here, or you can search up here by name. I am going to be using a Rogers RO4350 for this experiment. Earlier today, we worked with Teflon, and you can find that down here if you feel so inclined. But I know that this particular design works with Rogers 4350. You can change the color of it if you really feel like it. It's not important. And now we've got this maroon-shaped box that's the wrong size. So notice under the Model Builder tab that we now have a solid that is made out of Rogers 4350 instead of vacuum, and its name has been changed to substrate, but it's still the wrong size. So we're going to give this we're going to parameterize the dimensions so that we can change them later. I don't want to just say it's 10 millimeters long and then need to go back and change that at the end. What I'd like to say is it is substrate long, and then we can give substrate a value. So watch this. We're going to do negative substrate divided by 2, comma, negative substrate divided by 2, comma, 0. So these are our x, y, and z coordinates. It's negative substrate divided by 2, negative substrate divided by 2, and 0. When I hit enter, it's going to ask what substrate is. For this demonstration, we're going to say that substrate is 650 millimeters. Be sure to put the value, otherwise it'll give it no units. So hit OK. Our x size will be substrate. Our y size will be substrate. And our z size will be negative thickness. Press enter and it'll ask what thickness is. Say 125 microns, that's UM. Hit enter and hit enter. And now we're so zoomed in we can't see anything. So we can use these buttons up here, this button, fit all, and it'll show us everything that we've made and it'll fit it within our window. We have made a big flat rectangle. We can rotate around and see that it's pretty flat. We want to draw an antenna on it. So we're going to go up here to this drop down called Draw, and we're going to go to this user-defined model. The antenna toolkit has all the antennas we could need. We're going to go to Spiral and do an Archimedean spiral antenna. Go to Parameters, and we're going to change a few things. We used rad in for our inner radius, and for now, just put 34 millimeters as our inner radius. I think we did one that was 68 millimeters in the demonstration earlier. It doesn't really matter right now, we're just demonstrating. Turns, for the number of turns, we're going to keep at 1.5 for now. Expansion coefficient, we will change to flare rate and set that to 30 and hit enter, and we have created a spiral that is perfectly laid flat on our substrate. Look how nice. We need to do a couple of things. First of all, these arms are perfect electric conductors, but the computer doesn't know that yet. So we need to click both arms, and it's really, you can only click one at a time. So if you click one and hold control, you can highlight both of them, or similarly, you can just go up here and highlight both of them. Right click and assign a boundary perfect E. This is, doesn't matter what you name it, it's nice if you name it arms. Sometimes you may have multiple perfect conductors. Now if you look in the Project Manager tab, we expand this, under Project 5, we have a boundary. It's our perfect E arms. Now our arms are perfect conductors. While we're here, we can click on our port, right click it, or similarly, we can go up here to model, to port, and right click it, and assign this an excitation. We're going to use a lumped port. I think on the student version, it doesn't show lumped port, it shows port down here, just port, and you pulls up another drop-down menu to select lumped port, but find lumped port. Most power sources are 50 ohms, so just leave it at 50. It's going to say we have no integration line. It doesn't know which direction current is flowing, so we need to select an integration line. You come here and highlight new line, zoom in till you're comfortable, and we're going to go from here, here, to here. And notice when I'm right in the middle, the cursor becomes a triangle, and when I'm not quite right in the middle, the cursor is a square. So we're going to go from where it's a triangle right in the middle, through the middle, to where it's a triangle on the other side. And now we've defined an integration line. This is the direction our current is going to flow. We're going to hit next and finish. So we have created the substrate with the antenna arms and an excitation on it. But we need to create a box around the model so that we can define planes where we take measurements, because this antenna is going to radiate outwards and we need to know where to measure that at. So let's go back up to this cube. We're going to create another cube. Remember, click, drag, click, drag, click. And we've now, under solids, created a vacuum named box 1. We're going to rename this airbox. It's good practice to have these little underscores in between words because HFSS doesn't like there to be spaces in between words. We're going to leave this as a vacuum. This is a good function down here, the transparency function. Look what happens when we change the transparency. We can see through this box, which is good. This is just an air box. We don't need to be able to see it, but we like to let the wireframe is there. But it's in the wrong place. Notice that it's not perfectly oriented. It's that's not where we want it. So we're going to create box, double click on create box, and set our position to negative substrate, negative substrate, negative substrate, and 2 times substrate, 2 times substrate, 2 times substrate. So what we've done here is we've made a really big, pretty square-shaped box around everything. If we look from the top, it's perfectly centered. We look from the side, perfectly centered. That looks good. We can click on airbox, or we can just click on the box. right click it, assign a boundary, radiation. And there's now we have a radiation boundary. And if we look under the project manager tab in boundaries, we now have our perfect electric conductors and our radiation boundary. Our excitations, we have our port, which is excited in the middle in this direction. I wish it was a different color. And now we need to run a test, but we need to tell HFSS what kind of test we're running. So we go to Analysis, right-click it, and add a solution setup. We're going to go to Advanced. By default, it is going to analyze at a single frequency. More likely, I don't know what Dr. Chen's project is for y'all, but y'all will probably be doing a broadband setup where you're going to test from some frequency to some other frequency. I don't remember what this one is optimized for, so let's set it from 40 megahertz to 600 megahertz. This right here, maximum number of passes, is important. Setting it to 10 is a good place to start. It's basically a how many number of iterations do we want it to take before it settles on a convergent answer. Too few gives a bad answer, too many gives too much processing time. 10 is a good balance. Hit OK. It shows that we're doing a test from 40 megahertz to 600 megahertz with 401 points. We're going to set this to fast rather than interpolating. Fast works faster. Hit OK. And I think we have done everything that we need to run a test. But we can check that. We can go up here to this HFSS dropdown and do a validation check. And it'll show us that everything has been done. We created our radiation box. We did the analysis setup. Our boundaries are all correct. The 3D model isn't, there's no weird overlaps and anything in materials or anything like that. So we can run a test. So what we'll do is we will press HFSS, analyze all. I forgot to save this one, so yeah, save your project. That's great. You can see down here in the bottom where there's a messages window and a progress window. The progress window is showing that it's running. I can tell you this analysis takes a long time, 10-ish minutes to run. And that's more than I think y'all want to wait. So I'm going to abort this for now and show you what it looks like when it's finished. This is the same model that I just showed y'all, made of the same material, the same size, the substrate's a different color, whatever. And I just ran and completed this test. And when you run a test, you will see this results node right here. And it's going to be, let's delete everything. It's going to be empty when you get it. The first thing we need to do so that we can see a full 360-degree radiation sphere is to right-click radiation, insert far field setup, and hit infinite sphere. We're going to change this right here, this 180 to 360. That's all we're going to do. Hit OK. We're good. I did it twice. You will see this right here, and that's all you need to do. So now, you can click on results. We need to, let's see what our antenna did. We'll right-click it, create modal solution data report, rectangular plot. And by default, it offers us a plot where we are going to sweep across the frequencies, all of the frequencies between the 2 points that we selected. And the output will be an S parameter, S11, and the unit will be decibels. Let's show the report. So this is our antenna's behavior. It's not perfect. It's really not even good. Well, this is pretty good. What we're seeing is a large dip, which shows that most of our radiated energy is being transferred to the antenna, which is good. And that's occurring at about 270 megahertz. So this is our window of operation from about 220 to about 300. That's not all we want to see. We also want to be able to see, let's go to the same place, rectangular plot, or VSWR. VSWR is unitless, so keep it at none, and a new report. And this shows us that we have a good VSWR. You want below 5 at these ranges and above. That's good to know. Let's also check results, far field reports. I think it's 3D spherical plot. And we're going to look at gain, total gain, in decibels. That's not the plot I wanted, although it is pretty. So right-click on results, go to far field reports and 3D polar plot, and we'll see total gain in decibels, new reports, and this is what we're looking for. What's going on here is our antenna is laid flat in this direction, also in this direction, and we are radiating upwards and downwards. So as we look at this, we are radiating in the positive and negative Z direction. That's what this tells us, which is pretty good. And these are some of the important plots. This shows us the directivity and the magnitude in that direction. So you can see it's at the peak, it's about 5 decibels of gain. And these are some really important plots. There's a lot of other plots that you can find in here, and a lot of different categories and different just parameters that you can measure. You can look at let's see if this is a good one. There we go, the 2D radiation pattern. It shows a slice of the radiation at an angle. There's a lot of stuff going on here. Dig through these results. Be sure to play around with a lot of these parameters in here and see how those change your results. Also note that you can, rather than sweep across frequencies, excuse me, you can come in here and antenna parameters report. You can sweep across, well, it's not letting me do it right now, but you can sweep across variables. There's a lot you can do in here. If y'all have any questions, please call me or text me or send me your model, and I'll help you out with anything you can.